Hi, in this video we are going to look into a chapter called Threads and Multithreading. So boys and girls, welcome to this operating system academic lecture series, and so far we have seen in our previous videos introduction and backdrop, services and system calls, and also process concepts. So in continuation of the process management, let's now look into another important aspect of process which is called threads. So essentially, thread is also equivalently very important as compared to process. So the agenda would be to look into what are threads, benefits of threads, types of threads, and a simple case study with regard to some thread library. Okay, so let's begin our discussion. Traditionally, if you see what is a thread, so if you see any operating system textbook or any literature, the most popular common definition that generally you find for threads is people will say thread is a lightweight process. Thread is a lightweight process. In my terms, I will write it in short as LWP. So boys and girls, this is the most formal and popular definition of thread that one finds in the textbooks of operating systems. So we need to understand what is the meaning of lightweight, why is it called lightweight. But before that, I would like to emphasize and tell the students that you should understand thread is also a process. Thread is also a process. Now in the previous lectures, we have seen what exactly is the definition of process. As part of the process structure, what are the important components of the process? As part of the process structure. So let's write it down. Process in the memory will consist of the following components. Will have its text or code section, okay, and then we'll have the global data section, and process will be associated with a heap for dynamic memory allocation and a runtime stack. The purpose of stack is for storing the activation records. These are the constituents of a process as part of its structure. So invariably, thread is also a process. The moment I say thread is also a process, does it mean that is thread also going to have all these components? That's the question. We need to understand that. Exactly speaking, thread will not have all these parts independently to itself. There are certain sections, there are certain components which are basically shared among the peer threads of the same process. And some components are independent to each that we need to learn. But why is it called lightweight? Some people say threads share the resources of the process and therefore it is lightweight. But that is not the exact reason for calling thread as a lightweight. Let me tell you. Essentially, the main reason for calling thread as a lightweight is it helps or facilitate faster context switching. Generally, when I switch from one process to another process, I will have to share the store and load the PCB, and the amount of time invested in loading and saving is enormous. On the contrary, if I have less volume of information kept in PCB or the control block, then the context switching time invariably would become less. Context switching time is directly dependent on the size of the control block, the amount of context information available. Less the context information, less the context switch overhead. And if I have less context switch overhead time, essentially the performance or the efficiency of the system will shoot up, will increase. So primarily, one of the main objective, one of the design goals of thread is to go for faster context switching. And when I can switch from one thread to another thread in a process faster, that is one of the fundamental reason for calling thread as lightweight. We are going to discuss about this. But before I continue and make you understand the exact meaning of lightweight, I will tell you what is the basic motivation for going in for thread, so that you can really understand how multi-threading actually evolved, how the concept of thread actually evolved, and what exactly is the meaning of thread. We'll see that. So let's understand. Basically, this motivation goes back to the time of era of client-server architecture. You can take this into reference. In a traditional client-server architecture, imagine, for example, I have some network, okay, and let's say I have some server machine and several clients. Here I have one client, here I have another client, here I have another client, and like that, several clients are connected to this network, you can imagine. All right. So this client 1, client 2, client 3, and so on, so on. All these clients are connected to the network. You can even imagine that these clients are diskless and this is a server machine. This is a server machine which is having a huge hard disk drive. And this hard disk drive contains some database or some resource, maybe web server or some resource. Now, essentially, I will have an infinitely running process here listening to some well-known service access point. This is a server process, some background process, server process, like a daemon. The job of this server process is to provide the resources that are available to the requesting clients. So invariably, it may happen that at some point of time, thousands of requests may come from the clients. Then how can this server process be designed? This is important point. How can this server process be designed to serve these requests? These server process can be designed initially to work in a sequential mode. Sequential server. Sequential, I mean, it will serve the request one by one. It will take the first request, satisfy it, reading the data and then formulating the segments, PDUs, and sending it to the client. If not, I mean, then it will take the second, and then it will take the third, and like that it goes on, sequential design. Then if not sequential, I mean, the problem of sequential server design is latency. Definitely the requests that are pending at the end of the queue will experience a lot of delay. Starvation, you can say, lack of interactiveness. To overcome that, people thought of going in for concurrent server design. Concurrency in server design, concurrent server design. Concurrency at the first time or the first level was achieved by using multi-process approach. Multi-process approach. Multi-process approach means the server process would see how many requests are pending. Let's imagine the request queue have several requests, some k requests. So what this server process will do is, using mechanism like fork system call, it will create k child processes, clone or create k child processes, and associate each request to each of these child processes. And using policy like round robin, it will provide time quantum to all the processes, and thereby it will improve the interactiveness. That's how interactiveness was supposed to be incorporated or improved by using multi-process approach. So boys and girls, for quite a long time in the traditional computing environment, this is how concurrency was achieved, by using multi-process approach. So this was prevailing for a long time until the size of the network grew to a large extent. So what happens with multi-process approach? What are the limitations or drawback of multi-process approach? As you know, when I use fork mechanism to create a child process, you know it very well that the child will be an exact replica of parent, means the address space in the child is the replicated copy. So that means I will have k copies of address space. I will have k copies of code section, data section, heap section, and stack section. And naturally, when the code is replicated, copied, the functionality performed by each server process, each of the child server processes is essentially the same. Functionality is same. So that was the worrisome point for the developers and designers. When the functionality is same, then what is the fun in having n copies or k copies of address spaces? Can't we have an architecture? Can't we have an architecture which will have one common address space used by all processes? And this was the idea, this was the motivation for the evolution of multi-threading, right? Instead of having n copies of address space, can't I have an architecture like this, which will have only one copy of address space to be used by all child processes? This was the basic motivation for the evolution of multi-threading. So most of the modern applications, the applications may be standalone applications. So let me write. These applications may be server processes. These applications may be client processes, because multi-threading can be applicable at the client side also, or it could be standalone applications. So multi-threading is applicable at these three levels. They are multi-threaded. Threads may run within a process, within application. Okay. So like these are the different things that happens in traditional multi-threading. But before I come to that, process creation is heavyweight while thread creation is lightweight. Can simplify the code, increase efficiency. These are the basic motivating reasons for going in for multi-threading. So this is what I am trying to say. This is a traditional heavyweight process. So my dear student, boys and girls, I am to say that the concept of thread is not new. Traditionally, in the heavyweight process also have a thread. So thread is generally denoted by a line of control, just a line. What does that line indicate? This line indicate the order of execution of the instructions within the code section. You know the code consists of instructions I1, I2, I3, so on, IK. K instructions. So these instructions are purely executed in a sequential manner, is it not? First I execute I1, then I2, then I3. Suppose imagine I3 is a branch instruction, so I will branch from here to here. So this curved line basically perhaps indicate a branch instruction. So that means if you imagine that in your code section there are no branch instructions, then that thread will be a straight line. So the reason for having a curvy nature of the line is to indicate the branch instructions within the code section. So by default, every heavyweight process, traditional process will also have a line of control and that indicate the order of execution of the instructions, and that is called thread. So now when I create a multi-threaded process, as I said just now, instead of having n copies of address space, I will maintain only one copy of address space like code, data and other resources. Plus, I will have independent environment for each thread for its own execution. So every process, every individual process I said which will be commonly accessing the address space will be called as a thread of execution. So that data, that specific portion which is needed independently for a thread, that environment which is needed independently for the thread, I will have its own copy. Like every thread will have its own set of registers, own stack, own program counter, because this program counter indicates which instruction it is supposed to execute in the code section. This may be executing instruction number 5. This may be executing instruction number 12. This may be executing instruction number 55. So each thread needs to have its own program counter. Each thread may follow its own flow of control for the functions. So each thread needs to have its own stack and registers. These are independently needed for this environment, is independently needed for this thread. So all these threads, so in the form of a block diagram, you can imagine this control like this. This is my process, and within the process I have individual threads of control. T1, T2, T3, all sharing common address space. This is the basic ideology, basic representation of a multi-threaded process. This is called a multi-threaded process. So boys and girls, there are certain sections which are shareable and there are certain things which are not shareable. Code, data, files, heap, global variables are shared among the peer threads of the same process. Same process, not different processes, obviously. And registers, program counter, stack is independently for each thread. Each thread will have its own independent copy of program counter, stack and register. So this is an example of multi-threaded process. So if I design my server process in this case, check. If I design this server process in a multi-threaded mode, I can achieve a lot of benefits. I can save a lot of address space, resource sharing, make the system design economical, cost effective, and there are multitude benefits as I am going to show you later point of time. Okay. So that is a basic motivation, basic ideology of multi-threaded server. So boys and girls, this is the architecture that we are going to follow as per 𝐂𝐬𝐿 textbook. This diagram is from 𝐂𝐬𝐿 textbook that shows the basic architecture for designing a multi-threaded server as in previous example. So clients will send the request, the server will be in a continuous listening mode. Look at that. Resume listening for additional client requests. So whenever a request arrives, it will create a new thread to service the request rather than a new process. So keeping in view of the benefits of multi-threading, most of the modern applications, whether it is server processes or client processes or standalone applications, wherever applicable, they are going in for multi-threading. So I will write down what are the important benefits of multi-threading. So here I can say benefits. The first, interactiveness or responsiveness factor will improve like anything. May allow continued execution if part of process is blocked, especially important for user interfaces. As I said, the major motivation for multi-threading is resource sharing. Threads share resources of process, that is address space, easier than shared memory or other message passing. So to create the IPC mechanisms for communication, I mean, if I go for IPC mechanisms, then it becomes very slow. Rather than that, I can have shareable global data to be shared between two threads that make the communication very easy. The system become economical. Scalability factor will increase, will improve. The processes can take advantage of multi-core architectures. Present day we are talking about multi-core architecture, is it not? Our processes are i3, i5, i7, one core is like one CPU. So if I have a multi-core CPU with 3 core, 5 core, I can create a process with 3 thread, 5 thread, and each thread can run on one core and achieve true parallelism, real parallelism. So can exploit multi-core architectures. Multi-core or multi-processor systems puts pressure on programmers. The major challenges for the programmers include dividing the activities, load balancing, splitting the data, that is divide and conquer like policy, to take care of data dependency, testing and debugging. What is the difference between parallelism and concurrency? Most often people think that parallelism and concurrency are same. Essentially they are not same. Physically they are not same. Effectively they are not same. Parallelism means implies the system can perform more than one task simultaneously. This is real parallelism, physical parallelism. Physical activities are being carried out in real essence, in reality, simultaneity. So parallelism implies simultaneity. So doing multiple things at the same time is parallelism. Doing multiple things at the same time. Dealing with multiple things is concurrency. Dealing. Supports more than one task, making progress. Like on a single core, by using scheduling, I schedule one task, preempt, then schedule another task, preempt, then third. Like a single person dealing with multiple activities is like concurrency. But if the same activities is being done by 3 or 4 people together, that is called parallelism. That is called parallelism. So dealing with multiple things by a single person, single CPU is concurrency. Doing multiple things simultaneously, that is called parallelism. Okay, so multi-threading can achieve both parallelism and concurrency. Like this is an example. On a single core, concurrent execution on single core system, parallel execution on multi-core, like I have 2 cores. So these 2 tasks can go on together. Here sometime T1, sometime T2, sometime T3, sometime T4, again like that it goes. So essentially this is the difference between real parallelism and concurrency. So types of parallelism. Parallelism can be achieved at data level or at task level. Distribute a subset of the same data across multiple cores and same operation is performed like addition or multiplication or subtraction on each of the data. Task parallelism is distributing threads across cores. That is like process, and this is like within a process data is distributed and done. Like this is same data parallelism and task parallelism. Same data being used basically on different cores by different threads. That is task parallelism. Okay. So that is about the philosophy of multi-threading. I would like to, before I continue with the types of threads, I would like to basically tell that one of the reasons for calling, like each thread has its own set of attributes, stored in TCB. What is TCB? Thread control block. Thread control block. Just like PCB, you have thread control block. But what happens is, relatively, the volume of information kept in TCB will be much less than the volume of information kept in PCB. An important point, boys and girls. The volume of information kept in TCB is less than the volume of information kept in PCB. So this means when I switch from one thread to another thread, it needs less time. It needs less time. Rather than in comparison to switching between 2 processes. When I switch from one process to another process, I will have to save the PCB and load the PCB. If the volume of information is more, it will take more time. If the volume of information is less, it will take less time. Okay. So this will right here, will facilitate, because of this reason, it will facilitate faster context switching. Between 2 threads. Thread switching overhead become less, and that is an advantage that will improve the performance of the system. So therefore, this is the reason, one of the reason for calling threads as lightweight. This is the major reason. Thread switching is super fast than in comparison to process switching. So that's why it is called lightweight. I can switch fast. Okay. So this will make the system perform better. overhead will decrease, efficiency will increase. So that is another benefit for this. Next, we look into types of threads. What are thread types? Generally, threads are of two types, user level threads and kernel level threads. What are user level threads? So please see here. So let me write rather here. Thread types. So essentially there are two types of threads. User level, I will call in short ULT, and kernel level, we'll write in short KLT. So point is, as you know, every processor in a multi-program environment will operate in two modes, is it not? So for example, if you call this as user mode and kernel mode. So here you have the operating system kernel, and here I have a user process. This is some user process. So what happens when I create, process creation is basically done by the operating system. So the whole of process management, creating the process, assigning the attributes, scheduling the process, synchronizing the process, dealing with deadlock on process, everything was done by operating system, and that was worrisome point for the developers or the designers of the, developers or programmers. The programmers were saying, what is this? Everything is done by operating system. We don't have any control. I as a programmer, if I want to assign some specific attributes, I want to deal with scheduling by myself, I cannot do it. I have that limitation. That flexibility was not there. So this was being reported as a weakness, as a limitation to the developers of operating system. Then the developers of operating system said, no worries, we will provide you flexibility in terms of threading. So threads that are created, managed at the user level without any intervention, without any support from operating system, without any knowledge of operating system, without any interference of operating system. Those are called user level threads. So again I repeat, threads that are created, managed at the user level without taking any support, without any involvement of operating system are called user level threads. So for example, here if I create some 3 threads, these are called user level threads. They are basically managed by a user level thread package library or a runtime environment. Here I will call thread runtime environment. That will basically manage the user level threads. That means the operating system will always view this as a process, not threads. Threads are not visible to us. This property is called transparency. This is one of the benefit, you can say, one of the important aspect of user level thread, transparency. Threads that are existing within the process is not known to OS. OS does not know about it. What OS sees is only process. The whole control of the process is now by thread control package or thread library runtime environment. It will manage it. So whatever amount of time the process was given by the operating system, that will be shared individually among the threads managed by thread runtime environment. Sir, what is the thread runtime environment? To give an example, one of the popular user level thread package which you are aware perhaps is Java threads. And naturally the JVM will act like your runtime environment. That's an example. Okay. So what are the benefits of user level threading? The major benefit of user level threading is transparency, flexibility to the programmers or in terms of managing the threads, assigning the attributes, scheduling everything. Okay. And most important advantage is fastest context switching. User level threads. Fastest context switching. Sir, why fastest? Because generally processed context switching is done by operating system by changing the mode from user to kernel and again kernel back to user. But now when I'm doing a switch from one thread to another thread in the user space, I don't need to perform mode shifting. I don't need to shift from user to kernel because OS is not involved in doing context switching. The thread package, the runtime environment of the thread package will be doing the context switching at the user space by using normal load and store instructions. I don't need any system calls. I don't need any mode shifting. So therefore, it becomes super fast. But at the same time, there is a drawback limitation of user level threading for which we have to go for kernel level threads. Suppose imagine one user level thread running on the CPU needs to perform some system call, needs to avail some operating system service or execute, for example, any IO operation. This IO will be done by operating system. So the moment this IO operation penetrates into the operating system kernel, the operating system realizes that the process need IO, not the thread, because threads is not visible to OS. So operating system realizing process need IO, it will result in blocking the whole process. The whole process get blocked, the other threads are active. The thread that has initiated IO, no doubt it needs to get blocked, but the other threads are active. But operating system is unaware of the other threads. So the other threads which are active, they keep on shouting and crying, but their hue and cry shouts, they will fall to the deaf ears of operating system. Operating system is unaware, so it will result in the blocking of the whole process. So the requirement of IO or need for any operating system service by one user level thread may result in blocking of the whole process rather than blocking the individual thread. That's a major setback, and to overcome that, we go for kernel level threading. Let the operating system be multi-threaded. Such operating systems are called multi-threaded kernels, so that I can have management of user level thread by corresponding kernel level thread. Kernel level threads can get scheduled independently and thereby activate the corresponding user level threads when one thread gets blocked, and therefore can result in non-blocking of the other threads. So that is the thing. So threads are of two types, user level and kernel level. So please read that. The user threads management done by the thread user level thread library. Three important user level thread libraries is POSIX threads, P threads, Windows threads, Java threads. Kernel threads supported by the kernel. Examples are most of the Windows kernels, Linux, Mac operating system, iOS, Android, they are multi-threaded kernels. Okay. So this is an example of user level threads and kernel level threads. So the moment I have multiple user level threads, multiple kernel level threads, don't you agree that we need a sort of mapping function here? Right? We need a mapping function. So possible mappings are many to one, one to one, and many to one. So naturally, many to one is pure example of user level threads. No kernel level threading. All the threads are managed by single kernel level thread. One to one is ideal approach. Many to many is also a possibility. So let's quickly go through which one use many. This is an example of many user level threads mapped to a single kernel level thread. This will result in blocking of the entire process rather than the individual threads. So multiple threads may not run in parallel or on multi-core system because only one may be in kernel at a time. So few systems currently use this. Examples like Solaris green threads and GNU project portable threads. That is many to one. This is ideal approach, one to one. Each user level thread is managed by one kernel level thread. Okay, creating user level threads creates a kernel thread. So many concurrent systems use this, and the operating system that uses Windows and Linux, one to one. And we also have many to many. Allows many user level threads to map to many kernel level threads, as you see in the diagram. It allows the operating system to create a sufficient number of kernel threads. And otherwise, this is not a very common approach. And these are two-level model. I mean, generally user level threads getting managed by kernel level threads is generally called two-level model. So some note on thread libraries. It provides a programmer with an API which you can use in your program to create the threads, manage the threads, and perform other activities. So the library is entirely in the user space, and the kernel level library is supported by the operating system. So I can have two types of this. So pthread, which is a popular thread packet provided by the POSIX standard IEEE 1003.1c, right, which is portable operating system interface for Unix. It is a specification but not the implementation. So API specifies the behavior of the thread library. Implementation is up to the developer of the library. It is most common in Unix operating system, including Linux and Mac. And this is a simple example of a program using pthread library package. I would like you to please let's go through this program. Let's go through this program, okay, to see what is being done. You just glance through the code before I start the discussion. Glance through the code to see what is happening or what is being done in this thread package program of pthread. Let's see this. These are the header files that has to be included. There is a global variable called sum, and there is a function called runner. There is a function declaration, argc_rv, thread id, thread attributes, and here is the attribute initialization function. Default attributes are initialized, and here we are using pthread create live API call to create the thread. So here we are creating the thread, right? Arg, you mean the first argument which is being provided as a value, like the value of n, you can say. And then after that, we are waiting for the thread to complete. Thread pthread join is another call, and then finally we are demonstrating the sum. So what is it doing? This is a thread ID, thread attribute, and this is a function which is being called by the thread, which will be activated as soon as the thread is created. So what is the thread making the computation? Here is the runner function which is doing. So whatever is the parameter value, we are converting ASCII to integer, and then we are computing the sum of this first n. Suppose this is a value of n, sum of first n natural numbers is being computed, and then we terminate the thread. That's it. So finally this program will print the sum of all first n natural numbers printed by or computed by the thread associated with the process. That means we are creating a thread, we are creating a process, and within the process we are creating one thread, and this thread is computing the sum of first n natural numbers. That is what is the functionality. So using the API calls, as you see here, pthread init, pthread create, pthread join. So I would appreciate if you are able to write this program, execute this, taken from the 𝐂𝐨𝐿𝐵𝐿 textbook, write it and check your response, and so that you can get a feeling as to how threads basically operate. So that's a simple example. All right. So see, this is a code for joining multiple threads. If there are multiple threads, this is how you can basically, just a second. Yeah, if multiple threads are there, this is a thread join workers of 5 different threads are basically waiting for 10 threads to join, 10 threads to complete. This is where we can. And there is something called thread pool. You can create a pool of threads to be used by different requests coming from the clients, right? Those who are familiar with network programming will definitely understand what is the meaning of the concept of pool. What is the concept of pool? They wait for the work to come. So this will make the system faster. Initial setup time can be reduced, make the system faster, usually slightly faster to service a request with an existing thread than create a new thread. Allow the number of threads in the application to be bound to the size of the pool. Okay, so these are some of the tools. So here there is a pool function, and using that you can create thread pools. Now there are certain issues that needs to be addressed in the design and implementation of threading, that is called threading issues. One is, these are design challenges, boys and girls. Semantics of fork and exec has to be decided. When I call fork, that will result in creating a child process. So when one thread call fork, is it the whole process to be replicated or only thread is to be replicated? That's a design challenge. Exec will replace the address space of the process with the new program code. So with thread, is it going to replace the whole address space or only corresponding to the thread? So these are the design challenges for this. How signal handling is to be done? It is in synchronous mode or synchronous mode. Thread cancellation of target thread. Is it going to kill only one thread or all the threads of the process? What about the issue of thread local storage and scheduler activation? So one by one we'll take up each of these and see what are the possibilities. So some operating system have two versions of fork. That is, create the whole process, that means have multiple threads cloned or only one thread gets cloned. So therefore that is the thing. Works as normal, replace the running process including all the threads. So all the threads will get replaced with the corresponding program. Signals are very popular and very important in the case of Unix and Linux operating system, which is basically a signal to notify a process that a particular event has occurred. And just like interrupt has interrupt handlers, we have signal handlers. Of course, signal is also like an interrupt. So signal handler is used to process the signal. So signal is generated by particular event, and the signal is to be delivered to a process. Now when I have multiple threads within a process, how are we going to deal with signal handling? That's a major challenge. So it can be default approach for dealing with, or it can be user defined. Default means whatever system design and define, and user defined means we can define how it is to be handled. So every signal has default handler that the kernel runs when handling signal, or user defined signal handler can override the default, just like in C++, the default constructor or overriding constructor for single threaded signal delivered to a process. But if I have multiple threads, then how are we going to? Here is the challenges. So where should a signal be delivered for multi-threaded process? That's a design challenge. As a developer, you and me have to decide whether the signal to the thread to which the signal applies, or deliver the signal to every thread in the process, or deliver the signal to certain threads, I mean a subset of the threads, assign a specific thread to receive all signals. These are the various approaches which are there that can be used by different thread packages or different operating systems. These are the possibilities. Okay. Thread cancellation. Cancellation implies terminating. So terminating a thread before it has finished is called cancellation. So thread to be cancelled is target thread. Two general approaches. Asynchronous cancellation. Terminates the thread, target thread immediately, that is asynchronous. Deferred cancellation allows the thread, target thread to periodically check if it should be cancelled or not. That is called deferred cancellation. So this is a code to create and cancel the thread. So the library call which is used for cancelling a thread is pthread cancel. Pthread create will create the thread and cancel the thread, and then join, wait for the thread to terminate which has been cancelled. And there is another thing called thread local storage, allows each thread to have its own copy of data. Suppose if you want some specific data to be used specifically by a thread, right, specific data part, that is called thread local storage. Useful when you do not have control over the thread creation process. So different from local variables. This is not same as local variables. Local variables are visible only during single function invocation, but TSL, thread local storage, is visible across function invocations. That is the fundamental difference between local variables and thread local storage. It is similar to static data, and TLS, thread local storage, is unique to each thread. Okay. So different operating systems that support the concepts of threads are Windows threads and Linux threads. I would appreciate from the interviews perspective, you can just go through as a case study how threads are created, managed in these two different operating systems like Windows and Unix. That like Windows API, what does a thread contain in one-to-one mapping, like a thread ID, register set. This is a thread control block, contents of TCB in the case of Win, and these are the context of the thread. Like that, Windows threads containing the primary data structures of the thread include executive thread block and kernel thread block, and the thread environment block. These are the three important data structures for threads in Windows operating system. This is just for a case study. Like this is the structure: E thread, K thread, and TEB. These are the important data structures. So like that, you can see for the case of Linux. So this is what I have a brief discussion on the ideology, the motivation, the benefits, the types of threads for the study purpose. Okay, because when it comes to the matter of scheduling, when it comes to the matter of synchronization and dealing with deadlocks, we either say process or thread interchangeably, because synchronizing communication between processes is same as communication between threads. Synchronizing among processes same as synchronization among threads, or dealing with deadlock handling is for process or for threads. So therefore I thought better we should have some idea with regard to what is a thread, how is it similar and different to process, what are the benefits of threads, what is multi-threading, right, and then how concurrency is achievable at the data level and the task level through multi-core architectures, and then finally types of threads, user level and kernel level threads. This background is sufficient enough. If you further want to dive deep into this concept, you'll have to do some programming using some packages like pthread package, or maybe Windows threads or Java threads. Okay. So if you have any questions at any point of time, you feel free to register on my Telegram channel. Okay, and you can communicate with me directly if you want, or in the group, or even you can email me on my formal official email ID khalil.khan@geeks4geeks.org. Okay. So next sessions will start with other chapters, other topics like CPU scheduling, and then after scheduling we'll deal with synchronization. Till then, take care, thank you and goodbye.